Welcome back to section 5 of chapter 7. This is the last real section in the chapter. We do have another one, which is just how to pick which of the tests we're going to use, kind of summing up everything we've done the past few sections. But in this section, we're going to be looking at alternating series, the ratio test, and the root test. So we have a few different things, but some of them are very, very similar to each other. So, start out by looking at alternating series. We've actually seen these already. In the very beginning of the chapter, when we were looking at sequences and series, some of them were alternating series. In sections 3 and 4, we were looking at series with positive terms, just because those are easier to deal with. Now we're going to add back in the negative terms to see what it is that we can do. And so, an alternating series comes in the form of it has this -1 to the k plus 1 or -1 to the k. The difference is the first term positive or negative. That's really all it is. Notice here with the k plus 1, we're starting at k equals 1 for both of these. If you start at k equals 0 or k equals 2, then the bottom one would end up being a positive, then a negative, then a positive, then a negative. But you can always just plug in the numbers -1 to an odd power is negative, -1 to an even power is positive. Anyway, so we get alternating series. From an alternating series, to test to see whether it's convergent or divergent, we use the alternating series test. Also called Leibniz test or Leibniz criterion because it's attributed to Leibniz, one of the creators of calculus, for coming up with it. So what it says is that for an alternating series to be convergent, first the limit of the terms not including that -1 must equal 0. And then second, the terms are non-increasing. That means that they either go down or stay the same. So what non-increasing means is that A1 is going to be greater than or equal to A2, which is greater than or equal to A3, which is greater than or equal to ... all the other ones down the road. So each step it gets a little bit smaller or stays the same. Now, generally speaking, when the limit goes to 0, it's going to be non-increasing. It's going to be decreasing. There are some really weird series that could have a limit going to 0 and yet still not be non-increasing, where it still goes up and down a little bit even though it's going to 0. But those are kind of weird. The only one I could think of off the top of my head would be something like the absolute value of the cosine of n over n, where it's always going to be positive, because again, this we're taking that positive term, not the negative. So that makes it positive divided by n, means it's going to be going to 0, but the cosine is always going to be going up and down, up and down, up and down. So it will hit things going positive, but again, it's kind of a weird situation. Generally speaking, when it hits this, it also hits the non-increasing part. We will look at the non-increasing part and how to test for that. Sometimes we test for it using just logic, and sometimes we can actually do a test using ratios to see, and we will see that. So, first of all, let's see if an alternating series, is convergent. This is the alternating harmonic series. It's the harmonic series, 1 over k, but it's alternating. So, to test to see if this is convergent, we just take the limit, is then goes to infinity of an, and the an that we're looking at is 1 over n. Like, we're not concerned about this part. We're looking at the rest of it, which is this k. It's a 1 over k. So we're going to take the limit as n goes to infinity of 1 over n, which does equal 0. We've seen that equals 0 all year long. And so that works. Then the non-increasing, one term is 1 over k, or 1 over n. The next will be 1 over n plus 1. When we have a bigger number in the denominator, that makes it smaller. So it's going that way. The other way of doing this is doing a ratio of the second number divided by the first number. So we could have 1 over n plus 1 over 1 over n, which we can flip and multiply. So instead of divided by 1 over n, that's times n over 1, which means we get n over n plus 1, and we're looking for that to be less than 1, which n over n plus 1 is less than 1. 4 over 5 is less than 1. 9 over 10 is less than 1. So that's less than 1, which means it is non-increasing, which means that the alternating harmonic series converges. And that's kind of cool because remember the harmonic series where it's all positive, it doesn't converge because it has to do more than just have the limit of the terms going to 0. We have to look at all of the partial sums. And so it's actually easier for an alternating series to converge than for a positive series to converge. So we can approximate the sum of the convergent alternating series. We won't find the sums quite yet. Some of them we can find. Some of them are a lot more difficult, but we can still approximate the sums very nicely. And to do that, we actually look to see how much error we get after a certain number of terms. And so with that, we have this theorem for the error estimate for a convergent alternating series. So first of all, it has to be a convergent alternating series. It has to meet the criteria that we just saw. And then with a convergent series, we can look at the nth partial sum. So say the third partial sum. What this is saying is that the error between the third partial sum and the overall sum is going to be less than the fourth term. It's less than the next term, whatever it is. So if we took the sixth partial sum, that's going to be closer than, like the error between that and the sum will be less than the seventh term, not the seventh partial sum, the seventh term. So if we were looking at, say, the alternating harmonic series, we could find the third partial sum. We could find S3, which plug in 1, we get 1, minus plug in 2, we get 1/2, plus 1/3. So the third partial sum is that, and that's going to be about 0.833. It's 5/6. Well, the error at that, and its absolute value, because the fourth term could be positive or negative, we don't care. It's just the error. It's going to be less than or equal to the fourth term, which would be 1/4. So we're going to be 0.25 away from this 0.833. So the sum S will be in between 0.833 minus 0.25 and 0.833 plus 0.25. Well, that's a pretty big gap. Let's take a couple more sums. We can actually figure out what error we want. So let's say we want an error of 0.01. We want our error to be less than or equal to 0.01. Well, that's 1 over 100. So that means that we would need the 99th partial sum to get that. So for that, we'd have S99 is going to equal 1 minus 1/2 plus 1/3 minus, I'm not actually going to do all those. And then the last one is plus 1 over 99, because the odd terms, 1, 3, 99, are positive, and that's going to be about about 0.698-ish, which means that the sum here would be plus or minus 0.1. So we would be less than that, would be about 0.688, and bigger than that would be 0.708. So the actual sum should be in between those two numbers. And in fact, the sum of this one is actually the natural log of 2, which is 0.693 something something something, which is in between there. So that's what it is. If we wanted to be even closer, we would just have to take a bigger partial sum. And so that's what it is. A lot of times, like here, we had the alternating harmonic series, and we just took a couple partial sums and showed the error. That's just for the example. Usually, you'll get an error. We need less than 0.0001. And so we need to figure out what partial sum we need to take. Now, don't be afraid. It's never going to be too far down. They get pretty small pretty quick, but then they don't change all that much. The further you go down, they change less and less each time. So the first thing we would need to do is we would need to make sure it satisfies the criterion that we saw. So we need the limit as n goes to infinity of the term, which is 1 over 2n factorial, needs to equal 0, which, as we're going to infinity, 1 over 2 times infinity factorial is going to be 1 over an absolutely huge number, which takes us to 0. So that's there. And then making sure it's less. Logically, every time we go, we're going to have 1 over a bigger number. It's going to be going down, but we could also do the ratio. We're going to have 1 over 2n plus 1 factorial over 1 over 2n factorial, which we can move 2n factorial on the top over 1. We can distribute this. This is 2n plus 2 factorial, which we can expand out to get, I'm going to erase this because I know that I have something coming up down below. So this denominator can expand out because this is 2n plus 2 factorial, which will be 1 over 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, but 2n factorial times 2n factorial cancels. So we get 1 over 2n plus 2 times 2n plus 1, which is less than 1 because we have 1 over these fairly big numbers. So it is non-increasing. More specifically, it is decreasing, which means that this will be a convergent series, which means that we can use our error analysis. So the next step, once we know that it is in fact a convergent series, we want to figure out what term gives us that value. To do that, we just want to figure out what the term numbers are. We're going to want to figure out the term numbers anyway to add them together. So we have the 1 minus 1 over 2 factorial, 1 over 4 factorial, 1 over 6 factorial, 1 over 8 factorial. We can calculate those out to get 1 minus 1 half plus 1 over 24 minus 1 over 720 plus 1 over 40 320 plus dot dot dot. We can keep going if we need to. We won't, because if we change these into decimals, we get this guy here, the 1 over 8 factorial. That is less than the 0.0001, which means to approximate the sum, we just need to add up these. I'd say it's the first three because it would be the S3, but notice here we're starting at 0, so it's actually the first 4 terms, whatever. We add these up. I would use the fractions to add them up to get 389 over 720, which is about 0.540 plus or minus 0.0001 will give us the sum of that alternating series. So we can approximate a sum. We're not going to actually find the sum, but we can approximate it. Which brings us to other types of series or other types of convergence would be absolute convergence and conditional convergence. So absolute convergence is when a series will converge when all the terms are positive. If we took an absolute value of all the terms and made them so that it was positive, they're all positive, and it converges, it will converge if it also has negatives in it. So all of the series that we were looking at in the past couple sections that were all positive numbers, geometric series, power series, all of those, if we make them alternating, or not even alternating, if some of the numbers were negative, they would still converge because they are absolutely convergent. There's another theorem or statement that says absolutely convergent series converge, which just seems a bit redundant to me. But if it's something that we were already looking at that converges and there's negatives, it converges because it's absolutely convergent. Now we also have conditionally convergent series. That's where it's sometimes convergent but sometimes not. Like the alternating harmonic series is conditionally convergent because when we take the absolute value of all of them to get the harmonic series, it does not converge. But the alternating one does, so it's conditionally convergent. There's a bunch of properties about these. Some of them are ones that kind of make sense, where if two series are convergent and you're adding them together, then you can add the sums together. It's also convergent. A multiplication one, things like that. Most of them, like, we're really not going to use all that much. You can see them in the text, but there are some properties there. And so anyway, so that's absolute and conditional convergence. Absolute convergence is nice because it means that anything we throw at it, it will be convergent. So now let's look at a couple more tests. We have a ratio test, which we've actually seen a little bit, like we've used it kind of here and there. But what the ratio test says is if we have a series of non-zero terms, we don't want zeros because when you start dividing with 0, weird stuff happens. So non-zero could be positive, could be negative. The limit, if we take the limit of the ratio of terms, the second term divided by the first term, or the term divided by the previous term. The limit as n goes to infinity of that equals L, which is just a number. If that's less than 1, the series is absolutely convergent. If it equals 1, we don't know anything about the series. The test provides no information. And if it's greater than 1, the series diverges. And then also, if it equals infinity, the series diverges, which doesn't really need to be case 2. We could just have it equals L, and hey, infinity is greater than 1, so could kind of lump that case 2 into that last piece of case 1. So how do we use this? If we have a series, we're going to take the second term, the n plus 1 term or k plus 1 term, divided by the k term. So in this one, I'm going to find the ratio first. So we're going to have n plus 1 over 4 to the n plus 1 divided by n over 4 to the n. That's the ratio. We'd use absolute values, but these are all positive, so it doesn't matter. And then we need to simplify this. So to simplify, just like we've been doing already so far today, the denominator we'd flip and multiply. So we'd have times 4 to the n over n. And then this denominator we can actually break up. 4 to the n plus 1, when we add exponents, that means we multiply. So that could be written as 4 to the n times 4. Then we have our times 4 to the n over n. Hey, look, 4 to the n's cancel. How convenient. And that gives us n plus 1 over 4n. We're going to take the limit as n goes to infinity on that guy. Notice I didn't have the limit in there. We were just working on the ratio. Now we take the limit. That limit will be 1 over 4. We've done infinite limits. Hey, we're looking at the degree and then the coefficients. Equals 1 over 4, which last time I checked is less than 1, which means this series converges. It absolutely converges, or converges absolutely. So that's how the ratio test works. Let's see a couple extra examples of this though. So here's one involving more polynomial type deals. We're still going to do it the same. We're going to take 3n plus 1 over n plus 1 squared over 3n plus 1 over n squared. We can move this guy up to the top. So multiply by n squared over 3n plus 1. We can distribute. That's 3n plus 3 plus 1 will be 3n plus 4 times n squared over n plus 1 squared, which n plus 1 squared will be n squared plus 2n plus 1 times 3n plus 1. Multiply these out to get 3n cubed plus n squared over 3n cubed plus 7n squared plus 5n plus 1. That's just distribution, just multiplying. Limit as n goes to infinity. Really, the only pieces we need are these pieces right here, which limit as n goes to infinity, this equals 3 over 3, or 1, which when n equals 1, we have no info on this test for the ratio test. We'd have to use a different test. we can actually use a comparison test with this one to the harmonic series to find out that it actually diverges. But that's something we've done in the past. But from here, you divide by n cubed, and then it cancels, and yeah. Next one, 1 over k factorial. We've seen one similar to this. Same thing, 1 over n plus 1 factorial over 1 over n factorial. That can multiply up to the top, so we have 1 over n plus 1 factorial times n factorial over 1. N plus 1 factorial, remember factorial is that number times all the ones below, so that'll be 1 over n plus 1 times n minus 1 times, so it's times n factorial over 1. N factorials cancel, so we end up with 1 over n plus 1, limit as n goes to infinity equals 0, which is less than 1, which means that the series converges. So that's the ratio test. It's really stuff that we've been doing already, looking at other things, but it's an official test that we can use to tell whether or not these series converge or diverge, or if we need to use a different test. And another test that we have is the root test. And this one's very similar to the ratio test. So here we're going to take the nth root of the nth term and take the limit as n goes to infinity of that. It's going to give us a number, or infinity, and L is less than 1. The series converges, absolutely. If L equals 1, we don't have any information. And if L is greater than 1 or infinity, it diverges. So that is exactly the same as the ratio test. Like all of that stuff is the same. So it's just how do we get that number? Once we have the number, we know what to do with it. And so this works really well when you have a variable both in the term and in the exponent. For example, e to the k over k to the k. We have the variable in the term and in the exponent. So we're going to find the nth term. Well, the nth term will be e to the n over n to the n. And then we'll take, so e to the n over n to the n, we can factor out the root. This is e over n to the n. We want to take the nth root of that, which is just going to cancel out that exponent. The limit as n goes to infinity. So again, exponent gets canceled out. We have the limit as n goes to infinity of e over n. The n gets huge, so we have e over an absolutely enormous number, which goes to 0, which is less than 1. So this converges. So the root test, again, it's done the same. You'll generally have things like this, or you'd have a sum of blah, blah, blah over blah, blah, blah to the k. Hey, that's the exact same. You just don't even have to worry about factoring it out. So the root test, it's not as versatile as the ratio test. You wouldn't use it as often, but when you have something to the n power, or specifically an n to the n power, I would be thinking root test. And so there's a lot that we saw in this one. We have alternating series, how they converge, absolute convergence, the approximation of a sum. We have root tests and ratio tests to test for convergence. And this is the end of this chapter for the most part. The last of the new tests, we're just going to be looking at how to use those. So Keep working problems, keep asking questions, and as always, happy mathing.